Hello guys, my name is Sabio Fashino. As promised, I will be delivering a video presentation of flood risk mapping and damage assessment using QGIS. Already, you should have the link for the data sets that we're going to use for this exercise. But if you don't, you can get the link by requesting from IUFMP or by other means. Maybe I can send directly to you, whichever way is convenient. So this is the link right now. I'm going to just copy the link and paste it in my paste. It's a Google Drive link. So I'll paste it and then I can access the data set I need. Now, in that data set there are several different types of data. There's raster and there's vector. We will be using all these data sets for this exercise. So to ensure that we get everything that we need, I will download the entire data sets. And unfortunately, the data set is about 2 gigabytes big, but that is even after compressing the original data sets. It used to be about 9 gigabytes, but it was compressed to about 2 gigabytes. So for now, I'll pause this video, and once the dataset is downloaded, I'll resume. So now I have the complete dataset downloaded. I have it in my C drive, a folder called Training, and another folder called OKOME datasets. In there, you see the raster data, and in there we have the OKOME DTM. And then we also have the OKOME auto photo, which is the picture. There, well, the image is still too large to be viewed, so I'll close that. Since we're using QGIS for this exercise, I will start my QGIS. So my QGIS has started. So I'm going to just start the project by creating a new map. So now I have my map view is clear and empty. I will right click on it and change the coordinate system, set custom coordinate system, and type for the one I want, WGS84/UTM31. This is the coordinate system that is the final coordinate system for the project, which is a projected coordinate system called WGS84 UTM zone 31 north. So I would okay to that. So that's as set the reference system of the environment. The next thing I would like to do is I would like to load the data sets that I need. So in here is my layer, and there I want to first of all add a group, and in that group I would have my vector, data, and then I will also add my second group. I'll call it my raster data. What I'm just doing here is I'm trying to organize the data set I'm about to bring in. So for my vector data sets, I'm going to select vector, and I'll click at the top here. I'll click the open data source manager. Now if you don't find it there, you might just want to bring some of the panes. You have to click on the panel that will allow you to see some of these tools. It's a toolbox actually, so it's not a panel. Advanced digitizing attribute toolbox. So one of them is gonna bring up this layer, data source manager toolbox. So toolbox with data source manager toolbox. If it's missing, this is what you want to click on to bring it in. For example, if it's missing, then you might want to go to your toolbox and check that, and that will bring it in. Now, if you don't want to open the data source manager by clicking on the icon, the alternative way to do so is to go to layer and data source manager. So it brings you to this data source manager browser, and from there you will be able to access the files that you need. So for our file, we have it under training, and it's called OKMe datasets. We have the vector, and we have here two different datasets. There is one that is a geodatabase, and there's another one that's the shape file. So if I try to bring in the geodatabase, inside there are multiple data. I can just drag and dump it in my vector, and the OKMe AOI, which is the only shape file, is already loaded, but the geodatabase is asking that there are several shape files within it. Which one am I interested in? So here we can see that we have building footprints, the major road, the minor road, the railway line, and the river. And I'm just going to select all if they are already not selected, and say okay, add everything in. Then I'll go to my raster datasets, and I will just select both raster datasets with the control and drag and drop them in. Oh, sorry, it's dumped in the wrong place. I'll drag and drop them in the raster group, so that way I can always switch off and switch on as required. So now I'm done with my data source manager. I can close it. So here is our data sets. As you can see, the data sets don't have the right theme and they are not looking very good. So I can quickly change the theme or the symbology of these data sets. Easiest way is to go to properties and to go to symbology, and then you can select the symbol that you need. For example, for the building footprint, maybe I want to use gray, and I say okay. So now you have the gray color. For the area of interest, OKMe AOI, area of interest, maybe I want to use an outline, red outline, and I'll say that's okay, so I can see the outline. For the major road and major road, I see main road topo. Let's select this. Probably I would like to change this to a yellow, more yellowish color. Nice. Okay. So that's major road. I mean, this is what we have digitized as major road. That might not qualify as major road in reality. For the minor roads, I can take maybe this topo road as minor road. Okay. And then the railway line, if I double click, or if I right click and I go to properties and select symbology, I can go and select my railway line. Maybe here I want to change the thickness of the railway line itself, so it's a bit thicker. Let's make it 1.4. Maybe 1.4 is too thick, so double click, and then we reduce that from 1.4 to 0.8. All right, so now we have that. Let me take out the So if I take out the raster data, then I have exactly this bounds. Okay, so we've managed to import our vector data sets, and we've also managed to import our raster data sets, and they are classified under two different groups, the vector data and the raster data. Let me just do something. Let me right click and rename this group and call it I don't know if it's possible. Okay, it's probably not possible to rename the group, so I'll call this raster, raw raster. So raw data set. That way I can separate whatever I've done with whatever I'm yet to do. So this I'll call vector raw data, so we know the one that we imported raw and the one that we're going to work on. So the very first thing we want to do is we want to clip our data sets such that they are within the bounds of the area of interest. Now think of this. Suppose that you have a big area and you want to conduct analysis on a selected tiny area of interest. You don't want to spend the whole time processing the entire data set, because it's then going to take a lot of time, running the process. So what you want to do is you want to narrow down your area of interest to the area that you are most interested in. So for that, we're going to clip the data sets, and I will create a new group. I'll call it right click, I'll add a new group. I'll call it clip vector clip data, and I'll also create another one. I'll call it raster clipped data, and I want to clip the data using the area of interest. So I'll start with clipping of the raster data. For me to clip the raster data, in fact, for me to work on the raster data generally, everything I need to do about raster data sets is contained within the raster menu at the top here. So for me to clip, I want to extract a portion of the raster data by a specified mask layer. So the mask layer, if I click on that, it says clip raster by mask layer. So if I want to clip the DTM using the area of interest, then I'll have to specify the area of interest. Please note that the area of interest has to be a polygon, and that's the only way you can clip. So area of interest, it's polygon, and then okay, my DTM, and that's all I need. Yeah, everything else can be left as default. Nothing else needs to change. And then I click on run. One thing that can change is the final clipped data has to have a name. So if I click here, I can say save to file, and in there I go to my training folder, and I'm going to create a folder called OK OMI processing. So that's going to be the data set for processing, and in there I'll have clipped data. Let's say raster clip data. So that way it's easy for me to organize my file. And in here I'll give it a name. I'll call it OK OMI clip. So then it's gonna just save it as OK OMI clipped, and I'll say, oh, let's change that name. Raster clip data. So we say OK OMI DTM clipped. All right, so that'll be clip data set. Then I can click on run. So the clipping is complete, but I think in our selection we actually selected the auto datasets, but named it as DTM. So since we needed to clip the auto dataset anyways, we will retain that, but we'll just rename this. So what I'll do is I'll remove this layer and I'll go to the location of that layer, which is in training. And this, hopefully, if you do the right thing and not if you don't select the wrong one like I did, you wouldn't have to do this. And I changed the name now to Kill Me Auto, and I can easily just drag and drop it to the raster clip datasets. Now it's gone to the wrong place. Raster clip datasets. Okay, so let's build this up. I'll drag this down and I'll drag one down, put that down, drag that down. All right, so we have added the clipped data sets, and now it's called Me Auto Clipped. So we'll do the same thing for the DTM, this time around correctly. Go to raster, say raster extraction, and then we say extract by mask layer and select DTM rather than selecting auto. Be sure to select the right one, and we'll select the Me AOI, and then we'll save. We can save the name to the permanent, so we'll call it Me DTM clipped and save. And run the process. So once we run, it takes a little bit of time for the algorithm to take effect, and that time depends on your computing power. So for this, my computer is pretty fast and it's done, and I have the Me at the top, but that's because I did not select the right group, so the system went to the topmost group. But I'll drag it now down to my raster clip. Right, so if I switch off the different layers, I have exactly what I need. In my raster clip, I have both my auto and my DTM. Yeah. It is important to know that there's a difference at this stage. There's a difference between DTM and DSM. In generating my DTM, I had to classify the ground points separate from the other kind of points. I had to classify the points, the dense points, for me to isolate the ground level from the other points data. And with that ground level, I generated a DTM. A DEM of the ground level is a DTM. A DEM of all points, irrespective of what kind of level that it represents, it is the DSM. DSM is just the surface, the top surface of, as far as the eyes can see, flying from the top. So we have the clip data set. So at this stage, we don't really need the raw data set, so we can either switch it off, or we can even just remove the group. Let me just remove the group. I mean, it doesn't cost anything to remove the group. The data is still existing, but now we don't have too many unnecessary data sets in our collection. All right, so we're done with the raster clipping. Now we want to do the same for the vector clipping. So you would follow the same principle. I created this by error. Sorry about that. We'll follow the same principle for vectorizing the data sets, for clipping up the data set. To clip the data set, just like in raster, everything you need to do with vector is contained within vector. And we'll have it under geoprocessing tool, because that's what we want to do. And we have clip. So we'll select our input data set. In this case, we'll start with the building footprints, and we'll click using Okeomi AOI, and then we'll save so geo package. Now let's save straight away as a shapefile to avoid unnecessary complications. So we'll save the file as a shape, and we'll go back one step and create processing. We'll say vector clipped data, and then we'll call this building footprints. Run that. It takes a lot. It's a faster process to clip vector data than to clip raster data. So the algorithm is finished. Without having to close this page, we'll go back one more step. Select the next one, which is major road, and then we'll output the file. We don't need to, click on that. We can just put the file name there and call it major mgr road. Let's just say major road, and run. That's pipped. Then see, it's major road building footprint. Then we can do the same for minor road and change the name minor road. Minor road is created, and then we can do the same again for railway line. Then we can do the same for the rivers, the river pulley. So we can make this. Now we have the river, we have the railway, we have the minor road, major road, building footprints. We can move all of this data into our vector clip folder. So we can untick this group, and then we have that group that we need. Now, let me drag this to the top. We want our building footprints to be the first item at the top of the layer, and our river to be the one at the bottom, and then our road and railway and major roads might be just at the top of minor road, and then railway at the top of that. So we can then change the symbology again to match what we want, like we did earlier. Major road, I'd just like to change the color to yellow, and then minor road, so for that, sorry, railway line is this, major road, that's yellow, minor road is topo road, and then the river would have the river color, but I'd like to change the color a little bit to reflect more of a slightly lighter blue, something more in the color of the river. So this is our clipped vector. So do we still need this unclipped vector? Maybe not. Since we've already clipped it, we can as well just remove this unclipped vector from the system. So that way, what we need is what we have. So we have just what we need, clip to the area of interest, and that's complete the data preparation stage. All right, so now that we're done with the data set, the next thing we want to do is we want to generate an hydrological correct surface. What that means is that we're not exactly interested in the depressions, of the channels, the rivers. We're more interested in filling up those sinks so that we can then use that as a premise to identify the areas where water would actually flow to or through beyond those sinks. Now there is an algorithm called let me Google that. There's an algorithm called the sink fill by Wang Liu, and if you read up on it, there is a module in Saga GIS that is called fill sinks. So what you're doing is you're filling the sinks in the channels and any other depression that you don't exactly need. So that's what we're going to do next. But before we do that, we want to create a group. We're going to call that group. Oops, I've created another subgroup. So let me just remove this subgroup. I'll right click and create a group and call that group Raster processed. All right, just for us to identify the ones that have been processed from the ones that have not been processed. And in there, I'm going to put in the output from this DTM, the one I'm going to run the field sync module on. To run the field sync module, I need to have Saga installed. It should already be installed by default, but if it's not, anything that is a plugin that needs to be installed in QGIS can be done from plugins, manage and install plugins. So when you click on it, you will need internet access, and then you can go to all and then search for the name that you want. In this case, Saga. But I already have Saga on my system. I think Saga in itself is a full software by itself, so it's probably not a plugin, but it comes with QGIS. But there's Grass, and Grass too is it's almost like Saga for raster and vector processing. So for my field sync, I will go to vector, to raster, and it's gonna be very hard for me to find what I want to do from here. There are too many functions I need to run that I might not be able to see here directly. Now, also, anything that is QGIS related are the ones that are listed under raster, but any extra module that is not exactly QGIS but runs on a QGIS platform, for example, Saga or Grass or any of this extra software, then we'll need to actually run them through the processing toolbox. Now, if it's not already showing, you can access the processing toolbox by clicking on the panel, view, panel, processing toolbox, and that will bring up the processing toolbox on the right hand side. Here you can type fill sinks, and then you see that there are different field sync algorithms by different people at different times. The one we want to use is the field sync by Wang Liu, and the hydrology or the civil engineers can explain a lot more about the different how the different modules work. So I'll run the field sync, and for the field sync to run, I need to provide the system with the DEM. In this case, I'm going to provide it with OKOMI DTM clipped. The minimum slope, I can leave that as default. Then I'll save the field DM as, I'll save it as, let's create raster processed. I have double D's. Raster processed, and I'll call it, you know what? Let's just leave it as default. Yeah, let's leave it to save temporary. Then we can export it. I noticed that every time I try to save a file, it tries to save it as sdat. And in all honesty, I don't know why that is the case, but I know that, and that causes errors. So I know that if I don't save as to file and it saves temporary, then I can rename that temporary file and it will give me the TIFF file that I need. So let's run through that, and then we just click on run. So all we have to do is select the DTM and click on run. So the system will take some time, run a comprehensive algorithm flow, do some calculation, and then do all the field that needs to be done. I will pause the video while this is ongoing to save us some time. So now the field sync is complete, and there are 3 files generated as a result. So we have the flow direction, the watershed, and the field DEM. So we can close this field sync dialog. We don't exactly need the flow direction. We don't. So let me just disable this one here. We don't need the flow direction for our purpose. So we'll remove that layer. These are temporary layers. We don't need the watershed. So we'll remove the layer. What we need is the fill. You can see the slight difference between the fill. All the depressions around here have been filled to a great extent. So the elevation is almost uniform. And if there were any other depressions around in the areas where we don't need that is not has nothing to do with the river, for example, those areas too will be filled, and we will not have patches of fields of sinks in different places where they don't belong. So what we want to do is we want to focus on the area that is very close to the river and not include areas that are not. So the fill sync that we just run is most of the time necessary if we have areas with depressions. For example, area like query area where there are depressions around in different areas, it fills them up. But in this case, what we have as our raster data is good enough, that we don't need to worry about filling. I've run through this process to show you how to run the fill sync, although in our current case we might not even need to use it. All right, so let's just retain it and make use of it. What we now want to do now is we want to bring back our vector on top of the raster, and we want to find out around this area. I'll open up the raster auto mosaic. So we at this point here, we want to find out what the elevation is on the raster auto mosaic. I mean, what the elevation is on the DTM. So that way we can make sense to the elevation that we're going to use as our reference. So we know that somewhere around here, the flood normally overflows the, the bridge. We would like to find out what the elevation is at that point. The elevation at that point where the river crossed the road, on the road itself, is what we are interested in, and we can use that as our base point. Now, normally when you're running analysis, you need to have a reference height, an area where you want to walk, and then you need to have an idea of the depth of flooding at those areas for you to run a meaningful simulation of the entire area that might be affected by that kind of flood, and then carry out the assessment that you want to conduct. So we know that the road is our reference, and for us to get the elevation of the road, it's going to be a little troublesome to be taking out to be switching between auto mosaic and DTM and clicking on the identify. Where is identify? So we can normally click on the item we want to check the elevation for, and then we can just click on the area we're interested in. And because we have that item selected, it's going to show us the altitude around the elevation around that area. So here it's showing 206. If I'm to disable that, it still shows me the elevation. Now, there's another tool I can easily introduce, and that tool is called I already have it installed. It's called the value tool. Now, what that tool does is, irrespective of which layer has been selected, the tool allows me to see the different elevation at different on the different. It allows me to see the different raster values wherever my mouse is. If I click on it, it shows me this value to pin, and then anytime I take my mouse over anything, any of the pins that is active, that has been checked, it's going to be listed. As you can see, 219, 206 for the clipped Dtm on top of the road. Yeah, 207, 210, and the road keeps changing as we go up and down. So 206 around there, 199 down there, 206. So historically, on the road, they've had flooding as deep as 3 meters, close to 4 meters. So we're told, but we don't know that for sure. I mean, it's almost unrealistic to have such a flooding, but then it's assumed that it can be that high. And this is going by the information given to us by people that live around there. However, for the purpose of this analysis, we're just going to stick to a depth of 4 meters just to see, just for analysis sake. In reality, you're going to use a more realistic value that represents what you want to to analyze. So here we're going to use the value is 206. We're going to increase the depth to 2 by 4 meters. That means we want to see which area will get flooded if we are to work with 210 meters flood elevation. To install the value 2, you go to plugin manager, And like I mentioned earlier, you go to all and you search for the name value 2, and then you click on install if it's not already installed. In my case, it's already installed. All right, so now we want to do one more thing. We want to now extract. So now let's take off this vector. We want to from the DTM field, we want to extract the areas that are having elevation of 210. For this, we want to work with the raster. Like I said earlier, anything to do with raster is available in the raster menu. In this case, we want to do some raster calculation. So first is we want to work with DTM field, and we want to save the final output as under training, processing, raster processed. Okay, let's just call it flood level 210. And save. So it's going to save the output as that, as a GeoTIFF. Of course, you can select the kind of output you want, but in this case, we're just going to leave it as a GeoTIFF. And we say we want to put our, let's do it this way. Anywhere where field DM is less than or equals to 210, we want the system to make it 1. And anywhere that is not meeting that condition, and anywhere that is not meeting that condition, where field is greater than 210, we want to make it 0. And the expression is valid. And then we can run this. What we're trying to now do is we're trying to reclassify the raster data. So I'll pause the video while it's processing. So the process is complete, and we have the flood level 210N generated. I'll put that under raster processing group. Raster processed. And let me uncheck this and check that. So now we have classification, a classified area. So we have the white area represents 1, as you can see. If I select flood level and I click on that, represent 1, and the black area represents 0. The white area is the areas where the water level is anywhere between 210 and below, and the black area higher land compared to that low level. So with our results, we don't want this 0. We want to take it out completely. We don't want it. So to take it out, we export. There's a trick we can do. We can export this flood level. So we say flood area. Let's just call it flood area 210. It's going to be the final output name. Let's specify where we want to save that. It's going to be under Windows C, training, okay, processing, raster processed, flood area 210, save. And so we save that, but at the bottom we're going to define a no value. So anytime we see 0, we want to exclude it totally. We don't want it included, and then we want the data to be added to our processed raster processed when it's done. So I say okay, and the processing is ongoing. So now we have a 99% complete, and when it's done, it's gonna just add the data to the display. So we can already see flood area 210, and everywhere is kind of white at the moment because it's not displaying it yet. Actually, everywhere it's displaying it now, but everywhere is black. But it's a theme issue, you know. We're seeing everywhere as black. We shouldn't really worry ourselves much yet about what we see, but we should look at the layers and find out if what we have created has come in. As you can see, there's only one and there's no zero, so the one is black, and as such it's filled up the area that used to be white. So we can take off this one, which is the flood level that we had before. Remember that was white and black, and now the black area is white, and because it's overlaid, it perfectly covers everywhere. So we don't need this anymore. We can remove this layer, and it was more or less a temporary layer. And all we have now is just the polygon, the area raster data of just the area that is gonna get flooded. Now, for us to conduct any kind of meaningful analysis on this, it might be a good idea for us to vectorize it. But before then, let's see how it looks. If we change the symbology, we change the color to single band pseudocode. Let's add that and just call it 1, and then change this color to something more in line with the river. Say okay, and we apply, and we put our raster data at the top of so we can put this on the auto mosaic. If we put that below, then we can actually see areas that get flooded. Maybe we can also double click this and change the transparency to something more in line with, let's say, 50%, and then we can see the areas that are going to get flooded in the image. Yeah, but for us to conduct a proper analysis, we need this data set in vector form. So what we want to do is we want to convert this our flood area to its vector form. So to do that, let me untick this so it doesn't disturb us. To do that, I'm going to go to raster and I'll say conversion raster to vector. Raster to vector allows you to take your flood area to 0 and convert it to vector database. So let's go to training, create, let's say call it vector process. Let's say flood area 210 meters. Save. and then we can run the process, and it's done. So now we don't need a raster. Now we have a vector, and because we have the vector, we can change the color of the vector to, let's just give it a bound for now and say okay. And if we put other images there, you can see the areas that will get flooded. Let's change the bound and give it a feel of blue instead. So that's the area that would get flooded. But it's easy. It's easy for us to, and visually see the areas that are flooded. But for us to extract them, I mean, we need to be able to select them and extract them and run a batch analysis on them. For example, count the number of features that are affected automatically, or to export the features so that we can then conduct further, enumeration of those features. We need to be able to automatically select them. Now, to automatically select the features, either man-made or artificial, building ECC that's going to be affected, we need to use this vector to select, for example, the buildings that are impacted by the flood. So, to select the buildings that are impacted by the flood, it's a vector thing, and it's a research tool. We want to select first by location. Now remember that I'm not trying to intersect only, I'm trying to select by location, because if I try to intersect, then the system will cut this building into two based on the area that are intersect. So that is not what I want. I want to just select the building, any polyline. I want to select the complete polyline. I mean, any polygon. I want to select the complete polygon. So I go to my research tool, select by location, select the flood area. My input feature is my actual building footprint, and my intersect is what I want to use to select. Anywhere that intersects with the flood area, it should create new selection from there. So see, this building was just mildly affected by the flood. It was selected, and this one just barely escaped the flood, even though it's going to have issues with the road. It was selected. So now that we have it selected, we can, for example, right click on the building and export the feature, save selected feature. Only the selected ones will be exported. So we're going to save that as under training. Okay, processed, vector processed, affected buildings. I just put 210 into there so they know which of why was it affected, and then we can say okay. So now we have an extra. In fact, I'm gonna just create another group and call it process vector. And flood. So now we see all the buildings that are affected by the flood. So you can easily open the attribute table, and for example, all the information about those buildings will be listed. I mean, it's expected that the building footprint will have several attributes. For example, the number of the population of people living in the building, the owner of the building. Some basic information about the features will be listed in the database, and that would automatically populate based on areas that are affected. Yeah, based on the attributes that is selected. Now we also know that we have other things that are affected. For example, roads are affected, but if we don't, in the whole road, we don't want the system to automatically just select the entire road just because it overlaps. We want to cut out the area within the road that was affected, only the areas within the road that was affected, in case there will be a need to change the design or to work with. Now, for an example, I'm just going to run through with a major road and cut off the area that was affected by the flood if we have a flood elevation of 210 meters. So for us to do that, we go to vector, and what we're interested in is we are trying to extract. Um, we're trying to extract. We have under data management. Uh, Vector geoprocessing. Aha, intersect. Then we want to intersect. Our input feature would be the major road, but we want area that are affected by the flooded area 210 to be extracted from there, and we want to save the outputs as um, affected major road. Okay, then we can run that process, and that will give us affected major road. And we can then change the theme for that affected major road. So I just use the red color to reflect something like that. Just something to tell the difference. So we can see the area that has been affected by the flood. So we can do the same for the railway. If railway was affected, we can do the same for the internal roads, the minor roads. We can then get out, for example, the um, attribute table and see information. We can also do certain kind of analysis. For example, extract the length of this feature so that in case the information of the length is required, then it's possible to inform, to give meaningful information about the areas that have been affected. An excellent reporting can be generated out of this. So also is a map. The process for generating map is contained within. If you go to the training manuals for QGIS, you can see how to use the layout manager to create a new layout, an empty layout, or a report. Let's just create a map, for example, and call it one, and then you can bring in items. And so this, for example, is a map. You can bring in items and all that, and generate excellent display from there. So this is the end of the tutorial. At the end of the tutorial, we were able to during the course of this tutorial, we were able to import our data sets. We were able to generate a field sync DTM. We were able to extract the area that we consider liable to flood, and then we're able to extract the features that were affected by such areas, and as we were able to inspect their attribute table, and then we're able to also extract other features that are line features, rather by instead of by selection, but by we're able to extract them by intersection. And that is all that we have right now for flood analysis, flood risk analysis, and damage assessments. So from here you can see the area that will be affected. Obviously the upland is not significantly affected. However, there are other conditions that might impact our assumptions, and that will be addressed in the future.